Okay, today we're going to look at the speed of light. We've already realized that the speed of light is 3 times 10 to the 8th when you're doing calculations, but today we're going to figure out how they actually measured that and how that sort of changed over the years as well. So the first one we're going to look at is we're going to go back to Galileo times, and Galileo was sort of the first documented case of trying to calculate the speed of light. So what he did is basically he went up on a tall hill, he sent his lab assistant on another tall hill, and he said he's going to open his lantern and told his assistant that as soon as he sees his light, he wants the assistant to open his lantern. And then Galileo just said, well, if I know the distance between us, so in this picture that's at the bottom, we have 1 kilometer apart. He says, if I know the distance, all I have to do is measure the time that it takes for me to see the light when he'll measure the time it takes from when he opens his lantern to when he sees his other guy's lantern, and then he knows that he measured double the time. So he would do the total distance, and then he would basically divide by 2 times whatever time he measured between the two. But because he had lanterns which weren't very accurate, plus he only had like a pretty poor watch back in them days to calculate the time, he never got a very good answer. And he even realized, he said that this is likely not very accurate because it relies too much on human reaction time. So basically what he probably measured was just how quick he responded to seeing the light. Later on, so we're talking about 75 years or so later, astronomer Ole Romer from Holland, he actually noticed as he was checking out planets and moons and things like that, he noticed that the certain days there was a delay when he would see Jupiter eclipse one of its moons. So at certain points of the year, so let's suppose in July, he noticed that it was occurring at 1 o'clock, but then later on in the year, and in January, it was happening at 1:30 or something like that. So what he kind of proposed then is, we know that our distances are changing. So in this little map, if Earth is the green one and Jupiter is the orange one, when they're close together, we have a closer distance, but then later in the year, you can see the distance would be quite a bit larger. So Romer figured out that the time delay that we were getting with the eclipses were actually due to the distance the light had to travel to get us. And they had some rough ideas of how the distances were between the sun and the Earth and the sun and Jupiter and so on. So he used those rough numbers and did some calculations to get a fairly reasonable speed of light. And once again, he just basically did distance over time, and he just measured what the time delay was. He knew the distance change, so then from there he could figure out what the velocity of light was. And based on today's results, he was quite a bit off, but it was actually the first attempt to measure the speed of light that actually came up with a reasonable answer. Later on, so we're now in the mid-1800s, there was 2 scientists, and one happened after the other, but these are sort of the first cases now where we actually get pretty reasonable numbers. So a scientist named Fizeau, he actually came up with a pretty good way, and what he did was he basically just took a gear, so imagine sort of like the cogs on a gear, kind of like a little wheel, and so on. So what he did was he would shine a light, so he shone a light so that it would basically, the light would pass through the spaces on a gear. And then he would spin the gear, and the idea was that the light would pass through a space of the gear, it would hit a mirror, and he set the mirror up like quite a long distance away, about 8.5 kilometers. He wanted the large distance because they knew that light was traveling really fast. So he thought if they had a really big distance, that would give them a little bit better time to work with. So he would shine the light, it would go through the space of the gear, it would hit the mirror and come back, and he would change the frequency or the rotation of the gear so that it would just turn one cog to allow the light to go through. So if you imagine the gear spins, let me just erase this here a bit. So if the light's traveling and it goes through the space of the gear, and the gear rotates one tooth, the light would go through this cog, and then when it hits the mirror and reflects, it would actually come back through the next cog as it rotated. So all he would do is figure out the time that it took that to spin the cog one turn, and then he used that time to figure out what the actual speed of light is based on the distance that it traveled and the time that it took to spin. And he actually got a pretty good answer, so he was only about 5% off of what we accept today. Foucault actually took Fizeau's method and refined it a little bit, but instead of using a gear spinning, he used a spinning mirror. So the idea was same sort of thing. The light would hit a mirror, and he set these up at angles. So he had this mirror that was spinning. It would hit the mirror, and it would bounce off, and it would go, and he set it up even further. They thought larger distances would even be better, so he bounced it off another stationary mirror 35 kilometers away, and then it came back again, and then he made it so that he knew the spinning of the mirror, but when it came back, if the mirror was turned a little bit, so let's sort of imagine the mirror's at that sort of angle to start with, but then after the light bounces back, it's now going to be at a bit of a different angle, which would then reflect the light back at a little bit of a different angle again. So then he would just measure the angle. So he knew that if he could figure out the time it took to spin the mirror to change that certain degree of angle, then he could use that time to figure out the distance divided by time to get our speed. And he actually came up with a pretty solid answer that was pretty close to Fizeau's, but a little bit easier to do and a little bit better answer. The key was then Albert Michelson. So this is in the late 1800s. Michelson used Foucault's idea, but he used better quality mirrors, and instead of just having one mirror rotating and measuring the angle, he decided to use an octagon mirror or an 8-sided mirror, and he got a really good result. So he would take the light, he would shine it, it would hit the mirror, that would bounce off to another mirror that was 35 kilometers away, it would bounce back, and then he would see it through his telescope. And what he did was he figured out that if we could rotate the mirror so that the mirror rotated at the right speed, where it only turned exactly 1/8 of a turn, then he would be able to see the light. If the mirror was going too fast, where it turned too much, the angle would be off and the light would get bounced off. It went slow enough, the light might go the other way, and so on. So all he had to do basically was get the mirror to rotate at the right speed, and once he did that, then he could get the proper calculation. So let's actually do one of his calculations. So this one, it says we have a curved mirror 35 kilometers away, and he found that he had to spin the 8-sided mirror at 32,000 RPMs. So the question we're going to do is, what is the speed of light based on that information? Okay, so we know, let's go with our formulas. We know that our velocity is going to be distance divided by time. So the first thing is, how do we calculate the distance? Well, we're going to assume that the light and the telescope are right near the mirror, so we're basically just going to deal with the distance. So 35 kilometers, but it's going to the curved mirror and then back again, so we actually have a total distance of 70 kilometers, or 70,000 meters. So that's going to be our distance. Now we just got to figure out the time. So if we know that the 8-sided mirror spins at 3,200 RPMs, what we want to do is figure out what that is as time. So 3,200 revolutions per minute, right? So that's revolutions per minute. So what we want to do is change that to seconds. So 3,200 is how many turns in a minute. So if we divide that by 60, that'll actually give us per second. So 3,200 divided by 60 gives us 533 hertz, or per second. So then what we want to do is actually get times. Remember, time is 1 over frequency. So we'd have 1 divided by 533, and that gives us an answer of 1.87 times 10 to the negative 3 seconds. So all we have to do then is, we still got one little trick. Remember, that's the time for one whole revolution. We only want this to go 1/8 of a turn, so we actually have to divide that by 8 as well. So we end up getting 2.34 to the negative 4 seconds. So that's the number that Michelson would put in the formula, so 2.34 to the negative 4. So 70,000 meters takes 2 to the negative 4 seconds. We divide those out, and if we don't round off decimals, we keep things fairly close. We actually get about 2.986 times 10 to the 8th meters per second, which is pretty close. Our accepted answer of 3 to the 8th, we're getting those kind of numbers. So what happened is Michelson kept doing this over and over again to try to get better results. So he would change his distances, he would change his mirrors to be a little bit better quality, and he basically, after several tries, he's the one that came up with the 3 times 10 to the 8th number that we still use today. So this is in the early 1900s, and in 1907 he actually got the Nobel Peace Prize for his accurate calculations, and to this day we still use his method to calculate the speed of light, and the most accurate that's ever been measured to date is pretty close to what he calculated, and you can see we're just a bit under 3 to the 8th, 2.9979 roughly to the 8th, but if we round it off, we're still using the 3 times 10 to the 8th that Michelson calculated. And that's it for the speed of light.